So we're a couple of examples of finding sums of terms in geometric sequence. Again, there's two formulas. They're a little bit, the sum formula is a little bit more complicated, I think, for geometric than for arithmetic. But again, these are things that'll be given. I just want students to know how to use them as opposed to memorizing what they are. So the first example, something like find the sum of the first, 25 terms of, and then some sequence might be given. 4, 12, 36, 108, 324, ... So the recognition here is that as I go from term to term, the pattern is times 3, times 3, times 3. And the fact that there's this now constant ratio where I'm multiplying by the same thing from term to term tells me that it's geometric as opposed to constant difference, which was the vocabulary for arithmetic. So I've got this formula, sum, let me use a different color, sum equals first term, so that's 4, times 1 minus the ratio, which is 3, to the n, which is 25 terms, so 3 to the 25th, over 1 minus the ratio. And so for this one, all of the information that I need to find the sum is sort of given in the problem once I've recognized that it's geometric. And then on the calculator, I actually don't type the whole expression in. I type in the 1 minus 3 to the 25th first, and then multiply times 4, and then divide by 1 minus 3. And for problems of this sort, it's not unusual to get sort of these ridiculously large numbers because if I keep multiplying by 3 after 25 times, those numbers are going to be really large. An alternative way that a problem like this could be asked using this idea of sigma notation. This one's hidden a little bit. If you recognize that exponential function here, that's always going to imply geometric. But the other thing that you can do is you can expand the sigma notation by plugging in n equals 1, 2.5 to the 0 is 1, and so the first term would be 40, n equals 2, 2.5 to the 2 minus 1, so 40 times 2.5 is 100, and just plug in n equals 1, 2, 3, and so on to sort of see what the numbers in the sum are going to be. And hopefully, sort of recognizing the pattern, 40 to 100 is times 2.5, times 2.5, and so on. And so that 2.5 is going to be the ratio. And then in order to find the sum, I need to know 3 things. I need to know the first term, which is 40. I need to know the ratio, which is the 2.5, the base of the exponential function. I need to know the number of terms. And here, because it starts at n equals 1, 30 is the number of terms that I have to do top minus bottom plus 1, but when the bottom is 1, then that's going to be the number of terms over 1 minus the ratio. And again, calculator manipulation, and a pretty large number, 2.313 times 10 to the 13th.